Welcome to the Mechanics of Solid lecture series. In this next series of videos, we'll be solving some examples involving axial deformation, stress, and strain in various subassemblies. The lesson objectives, what I want you to be able to do at the end of this lesson, is evaluate forces and axial deformations in simple statically determinate systems, including subassemblies with tension members and rigid members, and segmented rods with or without internal loads. And also for those segmented rod problems, I'd like you to be able to analyze the force in the system by drawing an axial force diagram. Here's the first example we're going to look at. This is a little bar assembly as shown here. We have a rigid beam connected to two rods which act as axial force carrying members only and subjected to a downward load of 30 kilonewtons at the end. This is a statically determinate system. We only have unknowns. The only unknowns are the forces in these two internal forces in these two rods, which we can easily evaluate from equilibrium. Ultimately, we're asked to evaluate deformation in bars 1 and 2, downward movement of point A, and a factor of safety against yielding in each of the bars, which is also going to require us to consider the stresses. We're given the material properties of the bars, elastic modulus and a yield stress, the areas of the bars, and then all the information in the picture. And while we're at it, let's do a couple more interpretations. The length of each bar, bar 1 is 480 millimeters. The length of bar 2 is 600 millimeters. That will help us find the deformations in those bars. The axial force applied load at the end is 30 kilonewtons. To understand what we are asked to find, let's consider what happens when we pull downward. We expect point A will move downward and the whole thing will rotate rigidly. So maybe something like that. Probably we'll get downward movement at point B, which I'll label V sub B. And we'll probably get, we can check to be sure, but we'll probably get upward movement at C, which I'll label V sub C. And later we'll have to relate these to the axial deformations in the bars. Also, we expect to get downward movement at A, which I will label V sub A. Okay? So what we're asked to find, let's summarize that. Delta 1 and delta 2, the deformation in bars 1 and 2, positive for elongation, negative for shortening. V sub A, the downward movement at in bar A. And finally, a factor of safety against yielding, and so that's going to require us to evaluate the stress in bars 1 and 2, which I'll label sigma 1 and sigma 2. Our units that we're going to want to look at. For stresses, remember for standard units we like to express stress in megapascals, which is a Newton per millimeter squared. So we're going to want to convert forces to newtons and areas to millimeters squared. For deflections, we can calculate deflections in millimeters. Okay, I'm going to start with this factor of safety. It's easy to evaluate the forces and the stresses first, and that will help me figure out the deformations. First thing I want to do is draw an appropriate free body diagram. My free body diagram should include the internal forces, so I'm going to draw a diagram of everything above those cuts. Represent my beam as a straight line. I'll add the loads back in. At point A, I have my downward load of 30 kilonewtons. At point B and at point C, I have the internal forces. And one of the conventions that the book generally makes when you have internal forces is to assume they're in tension. draw them in the tensile direction, and I like this convention. If they're negative, it'll come out in the math. So I'm drawing them downward in tension. If they're in tension, those forces are pulling on the bar. Okay, so first, let's evaluate F1 and F2. Let's start with a moment equation about C to solve directly for F1. So the moment's about C, taking counterclockwise to be positive. We have 30 kilonewtons times the total length of the bar, 450 plus 225 is 675 millimeters. That's this total length of the beam. Okay, that's a positive moment about C. F1 also contributes a positive moment about C, which is the force F1 times the length between B and C, 225 millimeters, and I will set that equal to 0. Solve for F1 equals negative 30 kilonewtons times 675 divided by 225 millimeters over millimeters. Those units cancel out, and we get a negative 90 kilonewtons. The negative 90 tells me that F1 is really a compressive force. To solve for F2, I'll take the sum of the forces in Y, positive in the upward direction. Okay, working from left to right, I have negative 30 kilonewtons. I have F1, which is actually acting upward, plus 90 kilonewtons, minus F2 equals 0, and that gives me F2 equals negative 30 plus 90, which is 60 kilonewtons. That tells me it's in tension. From those forces, I can easily determine the stresses in the bar. Sigma 1 F1 over A1 is going to be negative 90 kilonewtons. I'm going to convert to newtons by multiplying by 10 to the third, divided by the area, 1,020 millimeters squared, and this gives me negative 88.2 megapascals. Likewise, sigma 2 F2 over A2, 60 times 10 to the third newtons over 520 millimeters squared, which is 115.4 megapascals. Okay? Finally, I want to find my factor of safety. We can define the factor of safety as the yield stress divided by the maximum stress that occurred in the system. We want to use the max of sigma 1 and sigma 2 to give us a minimum factor of safety. So our yield stress is 220 megapascals. The maximum of these two values, don't care about the sign, but the maximum value is 115.4 megapascals, and that gives me a factor of safety of 1.91, which seems like a reasonable value.